Hello, IB. You guys are on the last topic for this vector unit, and you guys have one topic left after this. So we are bringing vectors to a close, and we have been doing some real-life applications of two-dimensional vectors the last few days. So we're just going to take a look at how this looks with a three-dimensional vector. So some of these problems will look a little familiar, and then we'll do some that might look a little different. To start off, though, we're just talking about a regular vector equation, but we're talking about a 3D vector equation. So we need the x, y, and z component. And we discussed how when you guys have a vector equation, we need an initial point, and then we also need a direction. So for our initial point, I'll go ahead and just call that x sub 0, y sub 0, and z sub 0. And then we're going to be adding on the direction by units of time. So we have our t for units of time, and then we're multiplying by our direction vector, and we'll call this one ABC, whatever it happens to be. So our most important parts here are just recognizing that when you guys have a vector equation for three-dimensional vectors, you still have the initial position, and then you still have the direction as well. Direction or velocity vector in case you're not given a separate velocity. So this would also be your velocity vector if no other information is given. All right? And then you guys know we can pull out our parametric equations. So parametric equations would wind up just being each one individually. So we'll take out the x equals the x sub O plus AT. We have y is equal to y sub 0 plus BT. And then we have z equals z sub 0 plus CT. So the first two examples I'm going to do with you are actually very similar to ones that we just did in class today. So on our practice IB questions, you guys were working on the 38, 39, 40, 41, the later problems on that sheet. These two questions look exactly like two of them that we worked on today. So I'm going to work through these a little bit faster, and then I'll slow down when we have some newer material. But the next two problems I'll go a little bit quicker through. The first one talks about find a parametric equation, the equations for the line that's through these 2 points. So if you're going through 2 points, we can either start at one of them and go towards the other, or we could start at the other and go this way. Doesn't really matter, but we are going to use one of them as our initial position, and then we'll have to find our actual vector from A to B to talk about our direction. So I'm going to say that A is going to be my initial point, so that means my direction will be vector AB. And to find my direction, I'm going to do my terminating minus emanating. So I'm going to have -1 minus 2, 0 minus -1, and 2 minus 4. So my actual direction vector is going to be -3, 1, and then -2. So with my direction vector and my initial point, since I decided to start at A, I can go ahead and write my parametric equations. So I know that my x component is going to be initial point of 2 plus -3t. I know that my y component starts at -1 plus 1t. And then I also know that my z component starts at 4. And then I'm going to add on my -2t for my direction. So right here I have my parametric equations. Very similar to how we did this with two-dimensional vectors. We just now have that third component for the third dimension. All right, go ahead and pause here though if you need to double check and circle or mark any parts in your notes that you might need to ask Ms. Moore or myself about when you guys have us next time, all right? The second one I'm also going to go through a little bit quickly because this problem we also talked about today. In your notes last time we did the closest distance, and this problem talks about finding the coordinates of the foot. Now this is a new word, but the location of the foot is actually a place we've talked about before, of the perpendicular from the point. So I have a point that I'm calling P. That's -1, 2, 3. And then it says to the line with these parametric equations. So that means that there is some line that is being represented by those parametric equations, and we want to talk about the perpendicular. So I'm going to grab red. Okay? When we're talking about this scenario, this is really like a moving object passing a stationary point. So this is your moving object and stationary point example from your last night of notes. Right here, I know that my velocity vector for the line would be the 2. So velocity vector is going to be the 2, the 3, and then the 1 there. So 2, 3, 1. There's my velocity vector. And then I also know that my position right here, that position right there is the arbitrary position whenever this object gets closest to point P. So that's where the perpendicular hits. For that actual location, though, we're using our parametric equations to represent it. So this location, we're saying the x is 1 plus 2t, the y is negative 4 plus 3t, and then the z is 3 plus t. Okay? So that's my position when we are closest with that perpendicular right here. Okay? Boom. So my foot is actually right where I just pointed. The foot of your perpendicular is where you drop the perpendicular to the line. So here is the foot. Okay? So the question's just asking, find the coordinates of that foot. So I would still have to go through the work of doing the dot product of my vector from P to the foot with the velocity vector so I can find out what t is. Because if I have t, then I can substitute that in and figure out what the location of the foot is. So going through those motions, anytime that you have to go through this step anyway to find the shortest distance. So I'm going to take my velocity vector, which is the 2, 3, 1, and I'm dotting that with my vector that goes from P to the foot, so we'll call it PF, okay? Vector PF, though, since it ends at F and starts at P, in order to write a vector for it, I have to do F minus P. So that means I have to take the 1 plus 2t minus negative 1, and I have to also take the negative 4 plus 3t minus 2, and then 3 plus t minus 3. Okay? And let's go ahead through the motions. Go ahead and pause here and try to dot and set equal to 0. All right? Go ahead and pause the video, try that, and then push play in just a second. All right, so looking at the work, we wound up having right here 2 multiplies by 2 plus 2t, so that gives you 4 plus 4t. 3 multiplies by negative 6 plus 3t. And then 1 multiplies by t. We add them together, and then we simplify and solve for t. So t is equal to 1. Now if I know that t is equal to 1, I can go back and substitute in t right up here, since that is the expression for where the foot is. So if t is 1, my foot winds up being 3, negative 1, and 4. So we just have to look at what the actual question is asking, because this one wasn't asking for the closest distance. It wasn't asking for the time. So if I stopped at t equals 1, I would have just known that at 1 unit of time is when they're closest. So just depending, this one was actually asking for the location of the foot. So in this diagram, we have to be thinking about what are all the different questions that could be asked of us just from this setup right here. And from going through these motions, what could we find out? So here is a little bit of our new information. Aside from the examples that we did today, we are going to be talking about line classification. And I think it probably is easiest if you give yourself a little table with 3 columns, because there are 3 different ways. When we're talking about lines, we're talking about lines hanging out in space. So lines hanging out in space, they could be along an axis. I could wind up having a second line that intersects with it, but because there's a third dimension, 2 lines that look like they're intersecting from one viewpoint If you rotated them a little bit, you might notice a huge space between them. So in a three-dimensional world, the lines could not be intersecting at all, whereas if you put them flat on a piece of paper, like I had to draw on the smartboard, they look like they're intersecting. So what winds up happening, if you think about all of the different possibilities of what lines could be in space, there really only are three. And one of them is that they could be parallel to each other. So if you look at our diagram, this line here, okay, winds up being parallel to this line at the bottom. And that's going to be very hard for us to draw, and you won't be expected necessarily to draw that. We're going to attempt to next class. But it is kind of a tricky scenario to draw that. So we have two lines that are parallel to each other. If we want to show that lines are parallel, again, we're talking about the direction vectors of those lines, and we want to show that they're equal by a scalar k. So some of the work that would be entailed to show that would be to set our vectors equal to each other, our direction vectors equal, and they might be equal with a scalar k. All right, so we'll be doing that as well. We talked a little bit about intersecting lines. If you guys were doing example 2 last class with the torpedoes, the torpedoes were representing two lines that were intersecting. So just like this picture I drew up here, these wind up also being intersecting. So just like they are right down here. When they're intersecting, they're really only on one plane, so you're only talking about two axes. So you're taking it out of that 3D picture. They could be hanging out in 3 dimensions, that's fine, but really they intersect on a plane. So we're talking about that if they intersect at one point in particular, they have one point in common, that means that they have to share an x component and a y component, because they've got to be at the same place at the same time. So I'm going to mark that as well. Same place at the same time. Or if you guys think about when you go out and drive, right? You share the road and you share the same path as many other cars. However, you are hopefully not at the same location on the road at the same time as another car, right? Otherwise we collide. So if you think about that, if we have a path, we might share the same path. So we might share the same place, but we could also possibly be there at different times. So we could have same location, right? Same place, but different times. Okay? And again, that is going to depend on the actual, there we go. That will actually depend on the word problem that you guys are working with. So if you're trying to figure out if two cars intersect and actually collide, then yes, if they actually hit each other, they have to be there at the same time. Yet if we're just talking about two lines intersecting, if those lines represent paths, then you could have two paths that cross, but they could avoid an intersection, or they could avoid a collision, I guess, if they actually are not there at the same time. So we'll do a few like that as well. And then last but not least, in the 3D world only can you have skew lines. They're not parallel and they're not intersecting. They don't actually ever share the same place. So whereas intersecting lines have to have a common point, skew lines do not. They can be in completely different planes, and they could go about their business and completely pass each other and never realize the other one is there. So we have to show, in order to actually show that they're skew, we would have to think, well, if intersecting lines have to be the same place at the same time, so we set the components equal to each other. For skew lines, if we set the components equal, we would have to make sure that whatever answer we get actually doesn't make sense. So we would substitute our answer back in, and we would realize that no, they never actually do share the same point. All right? I'm going to go ahead and start one of the examples. However, you guys are going to really work with a couple lines next class, and you're going to work through all three of these. You're going to show that a line is either parallel or intersecting or skew. Two lines, excuse me, are either parallel, intersecting, or skew, so that you can really get a sense of what you're doing here. All right, so I want to show, I'm given these two lines in space, and we're using different variables for the different lines. So I'm using t as my variable for line 1 and v as my variable for line 2. And the reason for that is because they might have different times and they might have different places that they are. So we're not going to assume anything, so we'll use different variables for them. Since we're interested in showing that they're parallel, I've pulled out the two direction vectors, and I'm trying to show that they are equal by k. Go ahead and pause and see if you guys can find what k might be, if there is a k that works in this scenario. In this case, I took just an example of the x component, so 2 equals k times -1. In that case, k would be -2, and it does work for the rest of them.